First of all, anyone have any homework questions you want me to go over? Okay. So last time we talked about the Clausius inequality. Oh, before I get into this, two things. The first one is quiz 1 is going to be on Monday at the end of class. What? The date? 15th. No, 16th. And so the way these quizzes are, there's not going to be any calculations. It's just going to be short answer questions on stuff that I said in class. So to get ready for it, just go back and skim your notes, concentrate on definitions of things and things that say, notice this or remember this or whatever. But skim through everything. I try to focus on the big ideas and not the real minutia, but I'm just trying to encourage you to sort of make a framework in your head of the big picture ideas. And remember that these quizzes are always cumulative, so to get ready for these, you always want to go back to the beginning. It's not like just recent stuff. And then, sorry for the inconvenience, but no office hours tomorrow. There will be on Friday. But if you want to talk before Friday or you can't make it Friday, send me a message and I'm sure we can arrange a time outside of office hours. But Lake Conference Cross Country Championships, I have to be there. Okay, so now, last time we talked about the Clausius inequality. And the Clausius inequality says, for any cycle, if you add up all the heat transfer with positive going into the system and negative out of the system, like we're used to for the first law of sign convention, and divide it by the temperature where that heat is transferred around the whole boundary, you get something that's less than or equal to 0. And the important thing to remember is that this is for any actual process. So this is not like an idealization or anything. If the process is reversible, then it's equal to 0. And in the homework, this same idea is expressed this way. So you add up all those heat transfers divided by the temperature and set it equal to some negative sigma. But notice that means the same thing. That sigma would be equal to 0 for a reversible process. That's different than the definition of entropy. The definition of entropy is that a change in entropy from state 1 to state 2 is equal to the integral from state 1 to state 2 of dq over t for an internally reversible system. So this is an idealized process, and that's where the definition of entropy comes from. So entropy is, it's a harder thing to picture than most of the properties that we've talked about. It comes from this idealized process involving no irreversibilities. And then we talked about the TDS equations. So the TDS equations, there's two of them. You usually use one or the other, just depending on what variables you're looking for and what you know. So the first one says TDS, that's little s, that's the specific entropy, is equal to du plus pdv. And the second one says TDS is equal to dH minus v dp. And if you ever want to derive this in your head or whatever, you can think of an increment of the enthalpy is equal to an increment of the definition of, this is specific enthalpy, and the definition of specific enthalpy. So you get dH is equal to du plus dp times v plus p times dv. And then rearrange this as dH minus v dp equals du plus pdv. And then both of these are equal to TDS. Okay, so how are you going to use these? You always, in order to use these, you need stuff to be equal to 0, or you need to know some of these things. And so what we're going to talk about most of the time today is we're going to talk about how these simplify for incompressible materials and ideal gases. We're used to doing that. We're going to do it for this. Before I do that, let me talk about the problems for the Clausius inequality, like how to approach those. So let's say that a system operates a power cycle. So a power cycle looks like this, remember. You have the hot temperature here, system here, cold temperature here. I'll call this, say this is temperature TH, this is temperature TC. And the way a power cycle works is you bring in heat, QH, from the boiler, from the hot temperature. You eject heat, QC, at the low temperature. And the effect of this is that work is done on the surroundings. And so what you know from this is that all the stuff coming into the system, since it's a cycle, has to equal all of the stuff going out. So QH is equal to W plus QC. And then you can re-express the work just in terms of the heat. So work is equal to QH minus QC. The efficiency of a power cycle is what you're trying to produce divided by what you're trying to do the least of, the cost. So you have the work over QH. And you can rewrite this substituting in this expression for work from up here. You can rewrite this as QH minus QC divided by QH. So you get 1 minus QC over QH. And then if you have a reversible power cycle, an ideal power cycle, you can get your maximum or ideal efficiency for those temperatures by recognizing that the ratio of temperatures, what? Yeah. The ratio of those heats is the same as the ratio of the temperatures at the high and low temperature. So this is 1 minus TC over TH. So that's the highest efficiency you can get for a power cycle. Okay, and we're told that this system receives 1,000 kilojoules at a 500 Kelvin reservoir. And it discharges some unknown QC at a 300 Kelvin reservoir. And using this form of the Clausius inequality that says dq over temperature around the whole boundary is equal to some negative sigma. Determine the value of sigma if the efficiency is 0.2. Okay, well, we know that the efficiency of 0.2 is equal to 1 minus QC over QH. And so QC over, we're told what the QH is, that's 1,000 kilojoules is equal to 0.8. And so we know that QC is equal to 800 kilojoules. Okay? Are you with me on that? So based on the definition of the efficiency, we can calculate that heat transfer at the cold reservoir. Now we're going to use the definition, that Clausius inequality, the definition of sigma, and given that all of the all of the heat coming in is happening at a given temperature of 500 Kelvin, and all of the heat going out is happening at 300 Kelvin. So this integral we can just think of as the heat coming in, 1,000 kilojoules divided by 500 Kelvin, minus the heat going out that we just calculated, 800 kilojoules divided by the temperature at the cold reservoir. And so what you get if you divide that out is negative 666.6 repeating joules per Kelvin. From the definition of sigma, this is equal to negative sigma. And so sigma is equal to 666.6 repeating joules per Kelvin. It doesn't matter to me. You can do either one. So basically, the problems in the Clausius inequality stuff will have power cycles, refrigeration cycles, heat pump cycles. You're always going to use this kind of idea, You have the stuff that you know from the operation of those different cycles, this relationship between work, QH and QC. You have the definitions of the efficiency or the performance for the other ones, and you have the ideal efficiencies or performance if it asks you something about that, and then you're just going to use the definition of the Clausius inequality.
What exactly is sigma?
Well, it's just saying that, so it's related to the production of entropy. So it tells you something about how efficient or inefficient your system is. If you have a lower value of sigma, then you're not producing much entropy. If you have a higher value, then you're producing a lot of entropy. So you can use it to tell you something about how many irreversibilities or how serious the irreversibilities are. It's a way to kind of find out the different places that your system is inefficient.
So if I get it right, that's saying that at least you're going to lose 666 joules per Kelvin.
Yeah, I mean, I don't really have a good intuitive idea of what a joule per Kelvin is physically, but yeah, I mean, that's right. That's what it's saying. Like that ratio of joules per Kelvin, whatever that means, is kind of gone. You can't get that back. That's gone into the disorder of the universe.
So the higher that number is, worse.
The worse, yeah.
And does that sigma relate to the Stanford Boltzmann constant? Is that just radiated?
No, it doesn't relate to that. That's just, it's just that you only have so many letters.
It's confusing,
Yeah.
but we're using variables over and over and over.
Yeah, exactly.
Yeah, okay.
Yeah. Any other questions?
Does this work? I think one of the homework problems uses it. Does this
Yeah.
work when you're using like rates of heat change too?
Yes.
Okay, so that everything's the same.
That's right. So when it gives stuff in terms of rates, you can just think of it as like you're doing this, but for 1 unit of time.
Yeah.
And then it all works, you know?
Yep.
So yeah, you're just doing it for 1 second or whatever. It works exactly the same.
Alright, thank you.
Yeah. All right, so now we're going to apply the TDS equations for incompressible materials. To us, that's liquids. And ideal gases. Okay, so we're going to start with incompressible materials. And the definitions for incompressible materials is first, specific volume is a constant. Second, the specific internal energy is just a function of temperature. And if you combine this fact and the fact that specific volume is constant with the definitions of the specific heats of C sub P and C sub V, you get that C sub P and C sub V are the same thing. We'll just call it C, and that's equal to the total derivative of U with respect to temperature. Okay, so let's think about the first TDS equation. Remember, in any application, you're probably just going to use one of these two. So it says TDS is equal to du plus P dV. What do we know about this stuff? Well, we know that this term is going to go to 0 because V isn't changing. So, you know, dV is a change in V. Well, there's no change in V, so that's 0. Okay. And we know that we can replace du with C d temperature. That comes from this. Right? This equation can be rewritten as du is equal to C dt. And so now you can get all the S variables on the left side, all the T variables on the right side. And that lets you integrate. That C is just a constant, so you can pull that out. And you get that the change in specific entropy is equal to C times the natural log of temperature 2 over temperature 1. So for incompressible materials, you can calculate the change in entropy just from the change in temperatures. As long as you know that specific heat. Okay, so for example, let's say we want to calculate delta S for liquid water, as it goes from a temperature of 30 degrees Celsius to 80 degrees Celsius for a pressure of 10 bar. Okay, the pressure isn't going to have much effect on this. That's what we just learned. It's not going to have any effect on our calculation. It's going to have a minor effect when we look up the result in the table to check our answer. Okay, basically entropy for an incompressible material doesn't depend on pressure. So after we calculate it, we're going to compare it to the liquid water table.
Entropy is dependent on that just because it's not compressible, correct?
Yeah, I mean, that's right. So incompressible materials, it just happens that, that the entropy almost exclusively depends on the temperature, just like the internal energy does. It's not totally, I mean, that's an approximation, but it's a good approximation for liquids, for incompressible materials. Okay, so we're going to use a C value of 4.18, and that is in kilojoules per kilogram Kelvin. Okay, where do I get that value from? Let's go over that. So if you go to the tables,
Are you gonna have tables on the test?
yes. Yeah, I'll give you, I won't even make you really search for stuff. Like if you only need one line in the table, I'll just give you the one line, you know. So in problems where you have to find the specific heat, obviously you're gonna have to use that in this kind of stuff. Go to tables, go to the complete property tables. And it's this table A3, properties of common liquids, solids, and foods. And down at the bottom, it has the specific heat for water at different temperatures. So scroll down to table A3. There it is. You can see the specific heats over here on the right column. The temperatures it gives you are 0 Celsius up to 100 Celsius. Take the range of temperatures that's closest for your problem. You can see it varies a little, but not very much, you know. At 0 Celsius, it's 4.22. Well, and then it dips a little and comes back up. So I'm just using sort of the middle of the range at a temperature of 50 degrees Celsius. The specific heat is 4.18, and the units are kilojoules per kilogram Kelvin. Okay. So the change in specific entropy is equal to C times the natural log of the ending temperature divided by the starting temperature. Since that's not a difference in temperatures, remember that you have to use absolute temperatures for this. So, I mean, that's always going to be in Kelvin for us. So this is 4.18 times the natural log of the ending temperature is 80 degrees Celsius. So 80 plus 273 is 353 Kelvin. The starting temperature is 30 Celsius. So 30 plus 273 is 303. And you get a change in specific entropy of 638 kilojoules per kilogram Kelvin. To check this in the table, at a pressure of 10 bar, you get that there's one temperature. So let me write it like this. The specific entropy at a temperature of 20 degrees Celsius is 0.2961 kilojoules per kilogram Kelvin. At 40 degrees Celsius, you get 0.5715 kilojoules per kilogram Kelvin. You have to do an interpolation, and so that interpolation, you get that at 30 degrees. Well, since it's the exact midpoint of those temperatures, it's just going to be the midpoint between these. If you don't see that, you can just use the interpolation formula. And you get 0.4338 kilojoules per kilogram Kelvin. You can directly look up the specific entropy at 80 degrees Celsius. And that's 1.0737 kilojoules per kilogram Kelvin. And so the change in specific entropy is specific entropy at 80 minus specific entropy at 30, and you get 640 kilojoules per kilogram Kelvin. So you can see percentage-wise, that's a really good fit. You know, by using that simplified model, we got 638. The actual model from the actual value from the tables is 640. Any questions about that?
It's 640 joules, not kilojoules, right?
I think it's all kilojoules.
Wouldn't it be 0.64 then?
Oh, yes, you're right. There is a conversion in there. Thank you. Yeah, I'm sorry. Yes, I was trying to read off, make sense of what my notes said. So this is all converted to joules. Yes, thank you. Yeah, you're totally right. Yep.
What was the N? Well, I'm confused on that. C over N
C over N.
for the change in entropy? Or
That's-
Oh, I
specific-
can see
Natural log.
natural log, yeah.
Oh,
Oh, yes,
LN. Oh,
ln, yes. Okay. Oh, right, that's a natural
I
log.
could have been at like 4 a.m. So I'm like half figuring it.
I gotcha. Yeah, I mean, that comes from, so when we separated the variables in this equation here,
Yeah.
you know, divide both sides by t and you get an integral of dt over t, and that's where that natural log comes from.
Yeah, I was seeing it as a slash. And
No problem,
couldn't
yeah.
get beyond that.
Any other questions? Okay. So now we're going to do it for an ideal gas. And what do we know about ideal gases? We know the ideal gas law holds, where this R is specific to that gas. We know that just like incompressible materials, the specific internal energy is just a function of temperature. It doesn't depend on pressure much or anything like that. We know that the specific enthalpy is equal to U plus RT. And so that's also just a function of temperature. And for the specific heats, because of these two relationships, we can simplify CV as the total derivative of U with respect to temperature which means that you can write du as CV dt. And Cp is the total derivative of specific enthalpy with respect to temperature. And so we can also write dH as Cp d temperature. For ideal gases, both TDS equations give us something useful. So let's start with TDS is equal to du plus P dV. PdV okay, so hold on, let me, so I want you to notice a couple things. First, this we can write as CV dt, right? Second, we know that PV is equal to RT. And so we can write P as RT over specific volume. So this equation goes to TDS is equal to CV d temperature plus RT over V dV. So notice that we have the change in, we can write the change in specific entropy as a function of temperature and specific volume. And now let's go to the other equation. So we're going to start with T ds is equal to dH minus VdP dH, we know from up here above, is Cp dt. And this V, since PV is equal to RT, we can write V as RT over P. So TDS is equal to CPDT minus RT over P dP. So using this TDS equation, notice that you can express the change in specific entropy as a function of temperature and pressure. For small changes in temperature, you can assume that CP and CV are constant. We've seen this before just for calculating specific internal energy and specific enthalpy using those for ideal gases. So you can assume that CV and CP are constant. For larger changes in temperature, you can look up. Did I have that? You can look up these two constants in the ideal gas tables. So that's also, ideal gas tables are also something that are in those complete property tables. And what you have is this S0 of the later temperature minus S0 of the earlier temperature minus R times the natural log of P2 over P1. So these you're going to look up in the ideal gas table. So let me show you where those are. So go to the tables. Go to the complete property tables. And there are ideal gas tables, A17, A18, for all these different gases that could be useful. One of them should be air, which is basically nitrogen. There's also ideal gas tables for air on their own down here. So scroll down to, all the way to A17, 18, 19. And you can see that S super zero calculation. These are per mole, so be careful. Okay, so you want the ones that are not done per mole, but you can see that for a given temperature, you can just immediately look up that S sub zero that appears here. And that's a more accurate way to do this than that estimate based on the specific heats. Okay. All right. So let's do an example for an ideal gas. Let's say that we have air. We're going to treat it like an ideal gas. It's going to start with a temperature of 300 Kelvin and a pressure of 1 bar. It's going to go through a process that takes it to a temperature of 1000 Kelvin and a pressure of 3 bar. And we want to calculate delta S. First, assuming a constant value of C sub, the one we want is the C sub P. And we're going to assume that that's about equal to 1.005 times 10 to the third. That's kind of in the middle of that temperature range. And second, we're going to look it up in the table. We're going to look up this S sub 0 or S super 0 in the table. This is the more accurate way. This is the quick and dirty way. And what you're going to see is that for an ideal gas, the error in making that assumption over a big temperature range like this is going to be quite a bit bigger. You know, it still can give you some, like, sort of a useful idea, but okay. So let's, so we're going to start with this equation. So delta S is equal to 1.005 times 10 to the third times the natural log of the later temperature divided by the earlier temperature minus R for air is 287 times the natural log of 3 bar over 1 bar, so natural log of 3. And if you plug all this in, you get 894.7 joules per kilogram Kelvin.
How did we get, lab for first part?
Get what?
Natural law, 1.005 times 10 to the 5.
Oh, how did we get that CP?
For this,
The 1.05, that's just something that you have to look up in a table. So let's see, where would that be? Ideal gas properties, ideal gas specific heat. So table A2. So air, CP, right there.
so we're using the equation that we just have, right?
Yes.
So it's gonna be S, the raised to 0, T2 minus S raised to 0.
No, we're using the earlier form of this. We're using this one. Let me circle those two. These are the two. So we're using this one. You also could use this one. And this is this equation.
I thought.
Yeah. So let's see. You can think of, I mean, the definitions of these S zeros just come from integrating this divided by temperature, you know. So the definition of S sub zero would be like CP over temperature times the change in temperature. Okay, so now let's do the same thing, but using the more accurate way where we look up those S zeros. This was our first approximation. So delta S is equal to S0 at temperature 2 minus S0 temperature 1 minus R times the natural log of P2 over P1. If you look those values up in the ideal gas table for air, you get 2.97 times 10 to the third minus 1.702 times 10 to the third minus 287 times the natural log of 3, and you get a value of 952.7 joules per kilogram Kelvin. So percentage-wise, there's a lot more error in this approximation than there was for an incompressible material. But I mean, that's a big temperature range, 700 degrees Celsius temperature range, and we still got something that's useful for, you know, kind of back of the envelope type calculations. You wouldn't want to like expect a lot of precision or anything, but it can still give you something useful. And if your temperature range is smaller than 700 degrees Celsius, that only gets better. Okay. Okay, so basically today,
What's the safe range that we can use it?
I don't know. Yeah, but so practically speaking in this class, if you see on homework or a test a 5-degree temperature range or a 10-degree temperature range, that's me signaling that you can use that approximation. If it's hundreds, then you might as well just look it up in the table. The other thing is, the other way you know which one to use, practically speaking, in a class is if I give you one that you have the tables for, use the more accurate one, unless it's a very small temperature range. If I don't say what the type of gas is, you know, then you don't have a table to use and you'll have to use the approximation. Okay, so what we did today is we took those TDS equations and we figured out how we could approximate those for incompressible materials, liquids, and ideal gases. Okay, that is all.
I was thinking we don't have information so we can talk about problems and stuff with this.